StatQuest live stream, watching it's living in a dream. StatQuest live stream now. Woo! Hello, I'm Josh Starmer and welcome to StatQuest. Thank you for joining me. I see in the chat we've got all kinds of people from all over the place. We've got Egypt. I just saw Egypt go by. We've got lots of people from India. We got Poland, Colombia, Brazil, Uruguay. Anyways, lots of excitement, a lot of stuff going on. I'm just going to go ahead and get started because I'm super excited about today. So, bam. All right. Today we're going to talk about probability and expected values. And I'm going to take off my guitar. So there, bam. We're going to start crazy basic, but just hang in there. I know this intro probability stuff is going to be so simple that you might get a little bored, but whatever. We're going to plow through that stuff, and then we're going to dive in. Ooh, I just lost power. So I don't know how long I'm going to last. A transformer just exploded somewhere down the street. So we'll see what happens. If I just drop out, I will try to do this again tomorrow. But for now, we'll just keep plowing about through. Anyways, we're going to start off with simple probability stuff, but by the end, you're going to understand the concept of an expected value and how to calculate one. Okay, just so you know, probability and expected values are two of the fundamental building blocks for statistics. So if you ever try to figure out why something works the way it works, like why do we divide the variance by n minus 1 instead of n? Why does n minus 1 make it unbiased? If you want to understand the why of statistics, you're going to run into expected values all the time. It's sort of like the gateway to understanding all the kind of mucky things that lurk underneath everything that we do in statistics. Okay, so with that said, let's take a trip to the magical place called Statland. And if I had chimes, I'd have chimes going. Okay, so once we get to Statland, this guy, he's going to be our friend in Statland. He says, hey, I bet the next person we meet has heard of the movie Trolls 2. And we say, are you kidding me? Troll 2 is one of the worst movies ever made. Why would anyone know about it? By the way, I'm talking about the 1990 movie Troll 2 that if you look at it on Rotten Tomatoes, it is routinely rated as the worst movie ever made. So why would anyone know about that movie? Anyways, our friend says, I bet you $1 that the next person we meet has heard of the movie Troll 2. So we think to ourselves, we go, huh? Thinking. Good thing we have just asked everyone in Statland if they've heard of the movie Troll 2. And here's the data. Bam. There are two types of people in Statland. People that have heard of the 1990 terrible movie Troll 2, and people who have never heard of Troll 2. There isn't anyone who's sort of heard of Troll 2 or sort of hasn't heard of Troll 2. They're either in one group or the other. Each person has either heard of Troll 2 or they have never heard of Troll 2. They may not remember that they've heard of Troll 2, but they've heard of it. Okay, so 37 people in Statland have heard of Troll 2. And the remaining 176 people in Statland never heard of Troll 2. And that means there are 213 people living in Statland. So Statland is not a huge place. And looking at the raw numbers is useful because they tell us one, Statland is pretty small, and that whatever analysis we do only applies to a handful of people. So it's always important to kind of know what size population we're talking about. And by looking at the numbers, we can get a general sense of the trends. And in this case, we see that most of the people in Statland have never heard of Troll 2. But at a glance, it's not super obvious how the number of people who have never heard of Troll 2 relates to the total population of Statland. However, we can make this relationship super obvious by calculating percentages. So let's calculate the percentage of people in Statland that have and haven't heard of Troll 2. Actually, I have an itchy nose. I've got something. Well, I was going to say I've got something to show you, but let's keep going. I'll show it to you at the very end. Okay, so the percentage of people that have heard of Troll 2 is the counts, 37. So 37 people have heard of Troll 2, divided by the total, which is 213 people. So there's 213 people that live in Statland, and then we multiply that fraction by 100. All you guys know this. Everybody knows how to calculate percentages. And if you don't, wow, you just learned. So no big deal either way. Okay, and that tells us that 17% of the people in Statland have heard of Troll 2. Likewise, the percentage of people in Statland who have never heard of Troll 2 is the counts, 176, divided by the total, 213, multiplied by 100. And that gives us 83%. So we see that 83% of the people in Statland have never heard of Troll 2. Okay. Lastly, we can plug in the total counts, 213, into the equation as just the counts and the total. And that tells us that 100% of the people have either heard of Troll 2 or never heard of Troll 2. Alternatively, we can just add up the percentage of people that have heard of Troll 2, 17%, to the percentage of people who have not heard of Troll 2. That's 83%. And that should give us 100% of the people in Statland, because we said people in Statland are there's just two types. You've either heard of Troll 2 or you haven't heard of Troll 2. There's no other category. So that accounts for 100% of the population. Okay, percentages give us a good sense of how each subpopulation in Statland, and by subpopulation I mean people that have heard of Troll 2 or not, relates to the whole. However, it's important to note that percentages alone don't tell the whole story, and that we also need to know the total number of people to know if we're talking about a large population or a small one. So it's nice to know sort of the population size or the number of people we're talking about. Okay, now if we wanted to know the probability that a randomly selected person in Statland has heard of Troll 2, we simply divide the counts, 37, by the total, 213, and that gives us 0.17. Now, I told you this was going to be basic, so if you're fading out, don't worry, stick with us. It's going to get kind of cool pretty soon. Okay, 0.17, what does that mean? That means that the probability that someone in Statland has heard of Troll 2 is 0.17, which is pretty low, which means we're unlikely to just sort of run into someone randomly and they're going to say, hey, I've heard of Troll 2. The probability that a randomly selected person in Statland has not heard of Troll 2 is 0.83, which is pretty high. And that means that there's a good chance if we just randomly bump into someone that they're going to say, no, I've never heard of that movie. I don't care about that movie. So that's a pretty probable outcome. Okay, lastly, the probability that randomly selected person in Statland that has either heard of Troll 2 or not heard of Troll 2 is 1. So they're kind of guaranteed to be in one of those two categories. Now remember that bet our friend wanted to make. Our friend said, I bet you $1 that the next person we meet has heard of the movie Troll 2. And because we want to know the probability that we will win the bet, we're going to focus on probabilities. So let's move the probabilities to the top so we can focus on them. Okay, now, if the next person we meet has heard of Troll 2, then we will lose the bet. And that means we will lose $1. So let's put -1 here to represent the outcome of losing $1 if we meet someone who has heard of Troll 2. In contrast, if the next person has not heard of Troll 2, then we will win the bet. Hooray! And that means we will win $1. So let's put a 1 here to represent the outcome of winning $1 if the next person we meet has not heard of Troll 2. So now we see that the probability we will lose $1 is 0.17, and the probability that we will win $1 is 0.83. In other words, the probability we will win $1 is much higher than the probability that we will lose $1. So this looks like a pretty good bet for us to make. Oh, I just said that. So it seems like it would be a good idea to accept this bet. However, even though there's a high probability that we will win the bet, there's still a low probability that we will lose the bet. And no one likes to lose money, especially me. I'm not a betting person, so I'm going to be honest, this example is completely abstract. Betting is one of those things that some people do for fun, but it stresses me out. So I tend not to bet. So we say, can we make this bet 100 times? Or is this just a one-time offer? And I'll be honest, the reason why I'm saying this is if we just make the bet once, we could win or lose. We either win $1 or we lose $1. But if we make this bet a bunch of times, maybe on average we'll come up, ahead no matter what. Maybe, there's always a small chance we could lose 100 bets in a row, but that's a very small chance. And so I'd like to know is what's our chance of sort of what are we going to do on average over 100 bets? And our friend says, we can make this bet 100 times. So this is great. So what we're going to do is we're going to make this bet 100 times. We're going to ask 100 people. Okay. And so if we make this bet 100 times, we will win some and we will lose some. But we can use this table to figure out how much we will win and lose. And that'll give us a sense of what'll happen in the long term. How safe is this bet? Okay, if we make the bet 100 times, we can approximate how many times we will lose by multiplying the probability we will lose, 0.17, by 100. And if we do the math, we get 17. So that means we expect to lose 17 times out of 100 bets. However, just for now, humor me and let's not do the math and just know that this represents the approximate number of times we will lose the bet. Since each time we lose the bet, we lose $1, we can estimate how much money we will lose by multiplying the number of times we expect to lose by -1. So this whole term represents how much money we expect to lose in 100 bets. And if we did the math, we'd see that we expect to lose about $17. Wah, wah. Now, since we can make the bet 100 times, we can approximate how many times we will win by multiplying the probability we will win, 0.83, by 100. Again, if we did the math, we'd see that we expect to win 83 times, but we're not doing the math quite yet. Since each time we win the bet, we win $1, we can estimate how much money we will win by multiplying the number of times we expect to win by 1. So this whole term represents how much money we expect to win in 100 bets. And if we did the math, we'd see that we expect to win $83. If we wanted to find out the total of how much we could expect to win or lose, we can add these two terms together. And now, when we do all of the math, we see that we expect to win approximately $66 after 100 bets. However, we can also calculate the average amount of money we win per bet by dividing everything by the number of bets, 100. Doing the math gives us 66 divided by 100, which is 0.66. So, on average, we expect to win 66 cents every time we bet. Note, even though I win or lose $1 each time I bet, so I don't win or lose 66 cents, even though I'm betting $1 and I'm either winning or losing that dollar, on average, I expect to win 60 cents each time because sometimes I'm going to lose and sometimes I'm going to win. And so on. Once you average out the losses and the wins, we get 66 cents each time. In statistics lingo, 66 cents is the expected value for the bet. Using statistics notation, we would write E of the bet, or the expected value of the bet, equals 0.66. So that's how you notate that. And if we wanted to make it look even more cryptic, we would write E of x, or the expected value of x, equals 0.66. Where, in this case, x represents the bet, whether or not someone has heard of Troll 2. And I'm using this sort of fancy, cryptic terminology because that's what you're going to see if you pull up the Wikipedia article on any distribution. They're going to say, oh, the expected value, and they're going to say E of x equals something. And I just want you to know that E of x is really just an average. It's a type of average. And we're going to go through a bunch of examples. You're going to see the kind of different ways to do it. Okay, so we're going to put E of x, or the expected value of x, over here. And we're going to talk about why we left this math so messy. Because you remember, we could have done the math halfway through, but I said, let's just not do it quite yet. And we left it messy, and now we're going to talk about why we did that. Okay, since I'm multiplying each probability by the number of bets, and I'm dividing by the number of bets, 100, all of the values that represent the number of bets cancel out. And we are left with the probability that someone in Statland has heard of Troll 2 times the outcome, -1, plus the probability that someone has not heard of Troll 2 times the outcome, 1. And when we do the math, we get the same thing we got before, 0.66, because those hundreds just cancel out. So of course we're going to get the same result. Note, because all of the terms for the number of bets canceled out, the expected value simply represents the average of what we would expect if we made this bet a bunch of times. Now, if we made that bet once, we will either win $1 or we will lose $1. We won't win or lose 66 cents. But if we make it a bunch of times and we just average out the wins and the losses, we're going to get 66 cents every time we do it. So that's what this expected value represents. Note, in fancy math notation, this expected value is this sum. So it's the sum of each outcome, x, and we'll talk about what x means in a little bit, times the probability of observing each outcome, x. Okay, so for the first term, heard of Troll 2, the outcome is -1, so x equals -1. So that's what we're observing, is that we've lost some money. And the probability of observing the outcome of -1, of observing the loss of money, is 0.17. So we multiply those two values together. Then we add that term to the term for not heard of troll 2. And in this case, the outcome is 1. So x equals 1. And the probability of observing the outcome of 1 is 0.83. So we see the probability that x equals 1 is 0.83. Okay, so now we've seen how the fancy math definition of expected value works. So if you're out there in the wild, I usually don't like doing these fancy terminology things, but this is one of those things. But I'm going to be honest with you. Expected value, for a long time, when someone said, "Hey, we're just going to do the expected value," I'd kind of get chills down my spine, and I go, "Oh no, that's not good." And then they would show me this equation. I go, "What does that equation mean? I don't know." And that would intimidate me. So what I'm doing is I'm putting them on the screen to try to like demystify it. So we're going to plug in things for x, and we're going to plug in stuff for that probability a bunch of times. So hopefully by the end of this StatQuest, you're going to be real comfortable with this formula and you'll be like, "I get it. It's just a way of calculating an average." Okay, bam. Okay, now imagine our friend saying, "Because it is rare for someone in Statland to have heard of Troll 2, I will pay you $10 if the next person we meet has heard of the movie Troll 2. But if they've not, you pay me $1. Okay, so this is a slightly different bet. If they've heard of Troll 2, we get a bigger payout, but it's also rarer to find people that have heard of Troll 2. So there's a higher likelihood we're going to have to pay our friend. Okay, so we will win money. Will we win money or lose money if we can make this bet a bunch of times? So what's going to happen on average? Say like we could make this bet 100 times or 1,000 times. Overall, are we going to win money or are we going to lose money? So we're going to calculate the expected value to find out. Okay, this is the outcome for when someone has heard of Troll 2, so that's 10. And the outcome for when someone has not heard of Troll 2, holy smokes! Someone just did a crazy super chat. Andre Caravello, holy smokes! That's like the superest super chat I've seen in a long time. Dang, okay, sorry about that shout out, but I just had to do it. It totally caught my eye. I see a lot of chat going on in the background, and people are using the triple bam and the special emojis, but I had to shout that out. Okay, oh, where were we? And the outcome for when someone has not heard of Troll 2 was -1. Okay, when these are the outcomes, the expected value is, and we're using that fancy notation, the sum of each outcome, that's x, times the associated probability. So the probability that we observe that outcome. We'll start by plugging in numbers for heard of Troll 2. The outcome is 10, and the probability of observing that outcome is 0.17. Now we add the term for never heard of Troll 2. The outcome is -1, and the probability of observing that outcome is 0.83. So that's how we plug the numbers into that fancy equation. Now we just do the math, and the expected value is 0.87. And that means we expect to make, on average, 87 cents every time we make this bet. Double bam. Okay, I've got two more examples. I know we've been going pretty long. I've got two more examples using a 6-sided die. This first example is kind of the standard example. So if you go to the Wikipedia article on expected values, you're going to see this example. But now that you've got a better feel for expected values, you're going to see that example and you're going to go, I get it. I know how that works. Okay, so the probability, imagine we're rolling this die, and the probability of landing on any specific side, like having 5, like we have over here in the image of the die, is 1/6. Now, if we want to find the expected value or the average value of rolling the die a bunch of times, then we just need to plug in values into the formula for the expected values. And I think I skipped a slide, or it got deleted somehow. But you see that we get the outcomes are just the number that comes up on top of the die. So if we roll a 1, the outcome is 1. If we roll a 6, the outcome is 6. So those are the outcomes. And we're going to plug the probabilities and the outcomes into this formula for the expected value. So for lands on 1, the outcome is 1, and the probability of observing a 1 is 1/6. And that gives us 1 times 1/6. For lands on 2, the outcome is 2, and the probability of observing a 2 is 1 divided by 6. And that gives us 2 times 1 divided by 6. So we add that term to our sum. And for lands on 3, we get 3 times 1 divided by 6. So we add that term to the sum. And for lands on 4, we get 4 times 1 divided by 6. And for lands on 5, we get 5 times 1 divided by 6. And for lands on 6, we get 6 times 1 divided by 6. Now we just do the math. And the expected value for rolling a 6-sided die is 3.5. Note, there is no side on the die for 3.5, so we will never roll 3.5 exactly. But if we take the average of what we get after a bunch of rolls, then we expect that average value to be close to 3.5. Bam. Okay, one last example, and then we're going to be all done. Okay, here's the new bet. This is what our friend says. He says, I will pay you $100 if you roll a 6. Otherwise, you pay me $10. This bet means the outcome for rolling a 6 is 100 because he will pay us $100. And the outcome for rolling anything else is -10. So if we roll a 1, we owe this guy, our friend, we owe him $10. So those are our outcomes. Now, what's the expected value? All we have to do to find the expected value is plug the outcomes and probabilities of observing the outcomes into the formula. So, beep, beep, boop, boop, beep, 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 boop, 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 beep. Now we just do the math, and the expected value for this bet is 8.3. In other words, if we can bet a bunch of times, and not just once, if we can bet a bunch of times, we will win, on average, $8.30 each time. And that means our friend is the worst gambler ever. Triple bam. So that is, hold on, I think that's our last slide. I try to keep these things to about 30 minutes, and we're at 30 minutes. However, I just want to do a little shout out to Smriti Mehta. She just became a member, and that's awesome. That's super helpful for me and keeping StatQuest alive. Memberships are doing pretty well. We're almost up to 200 channel members, which is really exciting. And remember, channel members are a way to support me making StatQuest videos full time as a job. And the more time I can dedicate to that, the more videos and more live streams and more stuff you get. And I've got some exciting stuff to talk about. Last time we talked about how I was working on these Jupyter notebooks for how to do machine learning in Python. I've got a bunch of those made, and here's the deal. What I'm going to do is I'm going to start doing, because everyone's doing Zoom these days, I'm going to start doing Zoom classes. We're going to do a Zoom class where I take you through this Python notebook, this Jupyter notebook, and we're going to go through how to use XGBoost from start to finish. We're going to get some data. We're going to clean that data up. We're going to deal with missing values. We're going to make sure that the data is formatted correctly. Each type is correct. We're going to do all that. Then we're going to do XGBoost. We're going to optimize the hyperparameters. Hyperparameters is just a fancy way for things that you just have to tweak by hand. But we're going to call them hyperparameters because that makes them sound cool rather than things you tweak by hand. And we're going to tune those, and then we're going to have a finished model, and we're going to start doing those. So that's something very exciting to look forward to. I'm also working on the study guides, PDF study guides, and those are going to be downloadable. So lots of exciting things that are going on right now. And so I'm excited about StatQuest. I want to thank all of you guys for tuning in. Unfortunately, I rambled on for way too long today. So I'm unable to take questions live, but rest assured, I will save the live stream and I will go through it and I will look at your questions and I'll read through everything, and some may end up as a cue for a future StatQuest, a future live stream or whatever. I think we're going to stick with this probability for a little while. I want to do. I'll be honest. When I started this, my goal was to do conditional probability and sort of joint distributions and marginal distributions, and kind of talk about these sort of like weird kind of fundamental concepts that have a lot of scary terms associated with them, but are really basic. And once we do that, we can start heading into Bayesian territory. Then we'll start understanding Bayesian stuff. That was the goal. But when I was just kind of going, and all of a sudden I was like, wham, expected values are here. Let's talk about them, because expected values are a big deal, and I've been meaning to cover them because I've got a StatQuest on trying to explain why the variance equation the way it is. Why do we divide when we want an unbiased estimate of the variance? Why do we divide by n minus 1 instead of n, where n is the number of observations? And it all has to do with expected values. And so this is a stepping stone towards answering that question. So anyways, thank you very much. I'm really happy you guys are here. It means a ton to me. And I'm looking forward to the next StatQuest. It's going to be the first Monday in May. And I think we're just going to do them all at noon. It's a good time for me, and I hope it's a good time for you. I know it's not a good time for everybody, but these are recorded. And so if it's not a good time for you, you can always watch it later. All right, until next time, Quest on!